Hello everyone, hope you are doing very well. Today, as you all know, we are going to do the theory part 11 of the chapter Haloalkanes and Haloarenes. So, let's begin our today's topic NCRT chapter 6 Haloalkanes and Haloarenes, theory part 11. Specifically, we are going to cover the section 6.7.2. This is disclaimer. Objective. So today's lecture objective, after attending this lecture, you will be able to correlate the structures of haloarenes with various type of reactions, and you will be able to appreciate the applications of organometallic compounds. The topics we are going to cover today according to the NCRT, first of all the subsection 6.7.2 reaction of haloarenes. Then we will solve an example 6.9, and then we will solve the in-text questions 6.8 and 6.9. So let's begin our today's first topic, that is the reactions of haloarenes, in which first of all we will study the second major category of the reaction shown by the haloarene, that is electrophilic substitution reaction. Until now we have covered the reactions of haloarene followed by nucleophilic substitution. Today we are going to cover the electrophilic substitution reactions of haloarenes. Haloarenes undergo the usual electrophilic substitution reactions of the benzene ring, such as halogenation, nitration, sulphonation, and Friedel-Crafts reaction. So haloarenes usually undergo the electrophilic substitution reaction of benzene ring, such as all these kind of reactions, and we will look upon them one by one. Direct influence of halogen. Now, if you have a haloarenes, that means your aromatic ring connected with a bonding with a halogen. Okay, so what is the direct influence of that halogen on the reactivity or on that benzene ring? If you talk about it, halogen atom is a deactivating group. Okay, halogen atom is a deactivating group, but it is orthopara directing also. That means the incoming electrophile or nucleophile, that means incoming reagent that is coming for attack on the benzene ring, that is going to placed at the ortho and the para position. That means that is going to attack on the ortho and the para positions when the halogen atom is attached as a substituent on the benzene ring. Okay, so halogen atom is a deactivating group. Why? We will also see that. So halogen atom is a deactivating group. That means it deactivates the benzene ring due to its minus I effect, basically due to the its larger electronegativity and its ability to attract the electron pair towards itself from the ring. So halogen atom is a deactivating group, but it is also an ortho and para directing. Deactivating nature. Now its deactivating nature is due to the inductive effect. Okay, inductive effect, the or you can say the attraction of the electrons or shifting of the electrons away from the rest of the chain or rest of the ring towards the sigma bond. Okay, so deactivating nature is due to the inductive effect shown by halogens. Halogens are highly electronegative atoms. Highly electronegative, they have very high tendency to attracts the electrons towards itself and withdraw the electrons from the ring via the inductive effect and specifically minus I effect. Okay, so halogens, because they are very highly electronegative and they can withdraw the electrons from the ring via the inductive effect, specifically the minus I effect, which includes the electron withdrawing group, which is here also halogen, pull the electron density away from the rest of the molecule or rest of the chain, resulting in a reduction in electron density along the chain or along the ring. Okay, so due to the minus I effect shown by the deactivating group halogens, due to their high electronegativity and their electron withdrawing nature, the ring become deactivating. Okay, so the main reason behind this is inductive effect, specifically minus I effect. Minus I effect, minus inductive effect, makes the ring lesser reactive towards the electrophiles compared to the benzene. Now, if you compare the halogen substituted benzene ring with the benzene ring, where no substituent is present as halogen. Okay, so if you compare between the benzene and the halogen substituted benzene, that is haloarenes, minus I effect makes the haloarenes lesser reactive towards the electrophiles compared to the benzene ring. Because on the benzene ring, electrophile can easily attack on the benzene ring, okay, but due to the presence of halogen in the haloarenes and due to its higher electronegativity, halogen show minus I effect, attracts the or withdraw the electrons from the ring and makes the ring deactivating or lesser reactive towards the upcoming electrophile. Ortho-para directing nature. Now, the halogen show ortho-para directing nature specifically due to the resonance effect shown by them and the benzene ring. Okay, so lone pairs which is present on the halogens. So halogen is attaching directly with the carbon of the benzene ring, and there are lone pairs attached or lone pairs present on the halogen, which will going to participate in the resonance of benzene ring. So they will show plus R effect, positive resonance effect. So resonance effect increases the electron density at ortho and the para position. Specifically, if you draw the resonance diagram or resonating intermediate structures, you can easily see that due to the resonance effect, the electron density will increase at specifically ortho and the para positions of the benzene ring. And that is the main reason that's why halogen are ortho-para directing. Still they are deactivating, but they are ortho-para directing because their lone pairs participate in the resonance, that's plus R effect, and due to this the electron density is increased at ortho and the para position of benzene ring. Plus R effect directs the incoming electrophile to these position. Now, due to this positive plus R effect, that is positive resonance effect, the electron density increased at ortho and para position. So the incoming electrophile that have, which is you can say electron, which have lesser electrons. Okay, so it wants to attack on the position or on the ring or on the a point where there is lots of electrons present. Right, so due to this plus R effect and due to the increased density of electron at ortho and para position, the incoming electrophile will attack or will directly attach to these positions. You can also understand that this factor by seeing this diagram. This diagram consisting of 4 different structures showing the resonance effect, that is plus R effect, shown by the halogen. So here we have X as a halogen having lone pairs on it, and it is haloarenes. Okay, what will happen? These lone pairs of halogen participate in the resonance. So this lone pair will shift here, form a partial double bond character, and carbon halogen bond forms a partial double bond character, and this sharing electrons of double bond will shift here as a negative charge. Now again the shifting of the localization of negative charge happens on the ortho and the para position. So first of all, negative charge, the electron density increased at the ortho position. Then this negative charge will localized on the para position, okay, by just shifting the charges. So this is para position, and then this negative charge again shifts or localize at the ortho position. Okay, and final step will be that this negative charge will again go here as a double bond, and this partial double bond character breaks, and the halogen will get again its lone pairs, and the positive charge will stabilize. Okay, so these are the intermediate structures showing the resonance effect or resonance structures. Okay, they are equivalent because they all are deactivating. Okay, and resonance is happening, and the negative charge is delocalizing on the ortho and the para positions. You can clearly see. Okay, so here is one point to mention, that the negative charge or the electron density is not coming or it is not increasing at the meta position, right? It is only going on the ortho and the para positions of the benzene ring. Okay, so that's why, due to this factor, that lone pairs of halogen is participating in the resonance, showing plus R effect, due to which the electron density is increasing at the ortho and the para positions. Okay, due to which the incoming electrophile will direct at these positions, the ortho position and the para position. Okay, this and this are meta position, they will not affect due to the resonance. Halogenation. Let's see that halogenation is first of all the addition of halogen atom. Okay, you are adding the halogen atom. So halogen atom substitute the hydrogen atom. Okay, if you are doing the halogenation of your haloarenes, that means you are adding the halogen atom into them. So what will happen? The incoming halogen atom will substitute the hydrogen atom of the benzene ring and attach on the benzene ring. Halogen will act as an electrophile here. So if you are talking about, let's say, chlorine, so chlorine positive will comes towards the benzene ring, substitute one of the hydrogen atom, which is most reactive and which is most easy to substitute, and then place themselves at that position. Okay, halogenation happen in such way. So halogenation consisting of the addition of halogen atom in the benzene ring after the substitution of hydrogen atom, and the halogen will act here as an electrophile. You can see we have this haloarenes chlorobenzene, benzene attaching with chlorine. Now when you are doing the halogenation of chlorobenzene with the chlorine molecule in presence of anhydrous FeCl3 as in catalyst, you will got the mixture of products. First is 1,4-diachlorobenzene, where the upcoming electrophile, which is your chlorine ion. Okay, so chloride ion. So Cl positive here is electrophile, and when it attacks on the benzene ring, it will attack on the ortho and the para positions. This is very clear. We just have understood this, right? Due to the plus R effect, the chlorine, which is an electrophile, attacks on the ortho and the para positions of this ring. So you will get the mixture of product. First product you will get when the electrophile attacks on the para position, and you will get your major product as 1,4-diachlorobenzene. Along with that, you will also get a minor product, which is 1,2-diachlorobenzene, where the electrophile attacks on the ortho position. So due to the presence of symmetry in the para substituted, you can say haloarene, this 1,4-diachlorobenzene, where the chlorine electrophile attacks on the benzene at para position, will be the major product. Okay, and here in the ortho product you are getting as a mixture 1,2-diachlorobenzene. So this product having steric hindrance as a factor comparative to the another product, the para substituted product. So that's why the para substituted product is a major product. You will get this product in a larger amount comparative to the minor product, where the chlorine, which is an electrophile, attacks on the ortho position of benzene ring. Okay, so here the formation of electrophile, how electrophile forms in this process. So first of all, the chlorine molecule, the halogen molecule which we are taking, attacks or reacts with the catalyst, that is FeCl3, and the formation of a complex, anion plus a cation will form. So FeCl4 negative plus Cl positive. So you will get your electrophile, which is going to attack on the benzene ring because it is, you can say, unstable. It wants to stabilize by gaining the electrons by attacking as an electrophile on the benzene ring at the specific higher electron density positions, which is ortho and para, and you will get your mixture of products 1,4-diachlorobenzene and 1,2-diachlorobenzene. This is how halogenation happens. The one of the type of electrophilic substitution reaction shown by haloarenes. The next is nitration. This is also nitration reaction also happens via electrophilic substitution mechanism. So nitration involves the addition of nitro group in the benzene ring. Nitro group means NO2 group. So nitro group here substitute the hydrogen atom and attacks on the benzene ring and form the bond. Nitronium ion, that is NO2 positive. This nitronium ion acts as an electrophile here in this process. So if you have this chlorobenzene and you are reacting this chlorobenzene in the presence of HNO3, so you are reacting this chlorobenzene with HNO3 and concentrated sulfuric acid, you will get your mixture of products 1-chloro-2-nitrobenzene, where the nitro group, or you can say nitronium ion, attacks at the ortho position. So this is the minor product you are getting. And the major product is 1-chloro-4-nitrobenzene, where the nitro group is present at the para position of the benzene ring. Okay, so this is minor and the major product you are getting. So this is the mixture of products you are getting after the nitration of haloarene, that is chlorobenzene. Again, due to the similar reason that this para substituted haloarenes is having symmetry. Okay, if you pass like this is having a symmetry, and also in the ortho substituted product you are having steric hindrance comparative to the other product, the major product you are getting. Okay, so that's why your para substituted product, that is 1-chloro-4-nitrobenzene, is your major product. Here, the formation of electrophile. So how the electrophile is making, or how the electrophile is forming in this reaction. So your sulfuric acid is reacting with the HNO3 and you are getting H2NO3 whole positive complex cation plus HSO4 negative anion. Okay, so this is the cation and this is the anion you are getting. What will happen after that? The cation you are getting, that is H2NO3 positive, this is again dissociate into NO2 positive plus water molecule, and you will get your unstable electrophile that is going to attack on the more electron density positions of the benzene ring and form the major and the minor products. Okay, so this is how the nitration is happening in the haloarenes, where nitro group substitute the hydrogen atom and form the bond with the benzene ring, and here the electrophile is nitronium ion, that is NO2 positive. Next type of electrophilic substitution reaction shown by haloarenes is sulphonation. So sulphonation is addition of sulfonic acid group, that is SO3H. Okay, sulfonic acid group is SO3H, okay, or you can say HSO3. So when this group add on the benzene ring, then that means we are doing the sulphonation of haloarenes. Sulfonic group substitute the hydrogen atom from the benzene ring and form the bond with it. Sulfur trioxide act as an electrophile here, that is SO3. SO3 is a sulfur trioxide which is acting as an electrophile here in this sulphonation reaction. So you have this chlorobenzene in the presence of concentrated H2SO4 and a heating condition. You are getting your chlorobenzene as 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid, in which the 4-chlorobenzene sulfonic acid, the para substituted haloarene, is your major product. Other one is your minor product, where the sulfonic acid group is attaching on the ortho position. Okay, so these are the two products you are getting as a major and the minor group. Now here in this reaction, what is the formation of electrophile? So how electrophile forms? Here the sulfuric acid is going to dissociate into water molecules and SO3, which is an electrophile. So sulfur trioxide here act as an electrophile, attacks on the ortho and the para positions of the benzene ring and form the major and the minor product in the reaction. Okay. Now let's talk about the Friedel-Crafts reaction under the electrophilic substitution reaction. This reaction is used to attach alkyl group and acyl group. That means a single bonded carbon molecule attached with the double bonded carbon molecule. Okay, so Friedel-Crafts reaction we use to attach these two groups, the alkyl groups and the acyl groups. So there are two main types of this reaction. First is alkylation. First has the name alkylation, in which the addition of alkyl group happens. So alkyl group, that means R group, add. So alkyl group act as an electrophile here. R positive, that means alkyl group here act as an electrophile and going to attack on the haloarene. Okay, so we are talking about the first type of Friedel-Crafts reaction, which is alkylation, where the addition of alkyl group happens on the haloarenes, and also the electrophile here is alkyl group R positive. You can see we have chlorobenzene. It is reacting with chloromethyl CH3Cl. Okay, in the presence of anhydrous AlCl3, you are getting the mixture of products. The minor product is 1-chloro-2-methylbenzene and the major product is 1-chloro-4-methylbenzene, where the methyl group is substituted at the para position. Okay, so you will get this mixture of products, the minor one and the major one. The minor one have methyl group at the or you can say the alkyl group at the ortho position. Major one has alkyl group at the para position. Okay, so as we said that alkyl group addition is happening in the alkylation process, where the alkyl group is adding on the benzene ring, and also here the electrophile is also alkyl group, that is R positive. So the addition of alkyl group and the acyl group is happening in this alkylation Friedel-Crafts reaction. Now in this reaction, how the electrophile is forming? So the formation includes the reaction of methyl chloride, the alkyl halide, with the AlCl3, and the formation of electrophile happens. So AlCl4 negative will form as an anion and the CH3 positive as a cation, which we take as an electrophile, unstable electrophile, which is going to react or which is going to attack on the benzene ring to form the bond with it. Okay, and give you the major and the minor products respectively. The Friedel-Crafts reaction second type is acylation. Okay, now what is acylation? Where the acyl group is adding. Acyl group is RC double bond O. Okay, so acylation, where the addition of acyl group is adding to the haloarene, and here the electrophile will be acyl group, that is RC double bond O positive. Okay, so this is an electrophile which is acyl group, which act as an electrophile in this acylation Friedel-Crafts reaction. So we have this chlorobenzene, and when it reacts with CH3COCl, okay, in the presence of anhydrous AlCl3, you will get the minor product as 2-chloroacetophenone and the major product as 4-chloroacetophenone. The mixture of products you are getting, one is major due to this para substituted product, it is more symmetric, and the minor one is this, which is ortho substituted product. There is the steric hindrance comparatively. Okay, so here the RCO, R is your methyl group, so RC double bond O positive will act as an electrophile and going to attack on the ortho and the para positions of the haloarene. Formation of electrophile. Now in this process, the acylation Friedel-Crafts reaction, what is the formation of electrophile, how it forms? So this CH3COCl is going to react with AlCl3 catalyst, and you will get AlCl4 negative anion and CH3CO positive cation. So you are getting acyl group as a cation, as an electrophile, which is going to attack on the benzene ring of chlorobenzene and form the bond with it and give you the mixture of products, major and the minor one. Okay, so here also same thing is happening. Electrophile is attacking on the more electron density carbon, okay, or position of the benzene ring. Reactions with the metals. So there are some reactions of the haloarenes specifically with metals, in which the first is Wurtz-Fittig reaction. Okay, Wurtz-Fittig reaction, where a mixture of an alkyl halide and an aryl halide. Alkyl halide, that means Rx. Aryl halide, that means we have benzene ring and attaching with X. Okay, so these two mixtures when reacts with the sodium metal in the dry ether in presence of dry ether to give you an alkyl arene, then this reaction is named as Wurtz-Fittig reaction. What we are saying, we have aryl halide benzene ring attaching with halogen, right? And we have alkyl halide Rx. You are reacting them along with the sodium metal in presence of dry ether, and the reaction is happening and you are getting your product as alkyl arene after the addition of aryl and the alkyl group plus sodium halide you will get as a side product. The example, so let's say we are taking bromobenzene. The aryl halide here is bromobenzene plus you are adding the alkyl halide, that is methyl bromide here in the bromobenzene, and you are reacting them along with the two atoms of the sodium metal in the presence of dry ether. This aryl group, that is benzene, and the methyl group, that is alkyl group, will attach and you will get methyl benzene and sodium bromide. Your sodium halide will be eliminated and you will get it as a side product. Sodium bromide will be your side product and methyl benzene you will get as your major product in this Wurtz-Fittig reaction after the reaction of aryl halide with alkyl halide in presence of sodium metal. Okay, and in presence of dry ether you have to perform this reaction. Okay. The second type is Fittig reaction, where the haloarenes are reacting with metals. First is Wurtz-Fittig. Second is Fittig reaction. Now it is you can say some kind of similar, but what is the difference? Aryl halides here react with sodium in the dry ether to give the diaphenyls or biophenyls. Here the alkyl halide doesn't involve in the reaction. Okay, only you react the aryl halides with the sodium metal in the presence of dry ether and you will get your diaphenyls or biophenyls, both are same, as your major product. Okay, and diaphenyls, biophenyls are where two aryl groups are joined together. So in the Wurtz-Fittig reaction you are getting your product as a mixture of alkyl and the aryl group. In the Fittig reaction you are getting your product as a mixture of two aryl groups. What we are saying, we can understand through this reaction. So we are reacting the two aryl halide compounds, two aryl halide molecules. That means aryl halide means benzene ring attaching with the halogen, and we are taking two molecules of it, reacting it with the sodium metal in presence of dry ether and getting the product as diaphenyl, where these two aryl groups join together and give us a diaphenyl as a major product. Plus sodium halide will be your side product. For example, let's say bromobenzene, the same case. Now you are taking two molecules of bromobenzene, reacting it with two atoms of sodium metal. In the presence of dry ether, you are reacting them and you are getting your major product as diaphenyl. Benzene ring attached with benzene ring. Benzene ring bonding with benzene ring. Okay. So diaphenyl you will get as your major product after the joining of two aryl groups plus two molecules of sodium bromide you will get as your side product. So this is what in the Fittig reaction happening. Okay, so the major difference between the Wurtz-Fittig and Fittig reaction is that in the Fittig reaction we don't use alkyl halide. Okay, so we only use aryl halides, two molecules, and the product you are getting after the joining of those two aryl rings. Okay, meanwhile in the Wurtz-Fittig reaction you are adding the aryl halide with alkyl halide and the final product you were getting is the addition of the aryl and the alkyl group together. Okay, let's solve an example. Example 6.9. Although chlorine is an electron withdrawing group, yet it is ortho-para directing in the electrophilic aromatic substitution reactions. Why? So you have to explain that why chlorine is a ortho-para directing group in electrophilic aromatic substitution reaction. Meanwhile, it is an electron withdrawing group. Still, it is ortho-para directing. Why? You have to explain it. So you have given some time, try to analyze this question, and then we will see the correct answer. Okay, let's see. So for this example, first of all, we have to understand that chlorine is a halogen, it is an electron withdrawing group, we know. And why it is an electron withdrawing group? Due to the inductive effect. Inductive effect. Why it is showing inductive effect? So chlorine withdraws the electrons. That means chlorine show the inductive effect, destabilizing the intermediate carbocation forms and acting as an electron withdrawing group. So this is how the chlorine is acting as an electron withdrawing group after withdrawing the electrons and destabilizing the carbocation intermediate. So what is happening that you have this chlorobenzene. Okay. Now when electrophile is attacking on the ortho position of this benzene ring, the due to the inductive effect of the chlorine of the chlorine atom of the halogen, it will withdraw the electrons from the ring, destabilize the ring, and destabilize the intermediate carbocation forming. So this carbocation which we are getting after the withdrawing of the electrons towards the chlorine, positive charge comes at this carbon. Okay, so carbocation form, but this carbocation is unstable. So inductive effect is destabilizing the intermediate carbocation forming. Okay, and this is how the chlorine is acting as an electron withdrawing group. Now let's talk about the resonance effect shown by it. So chlorine donates its lone pairs through donates electrons through its lone pairs, particularly at the ortho and the para positions, stabilizing the carbocation. So along with the inductive effect, it also showing the resonance effect, which involves that the donation of the lone pair electrons, particularly at the ortho and the para positions of the benzene ring, via resonance. And through this, it is stabilizing the carbocation. So what we are saying, that let's say we have chlorobenzene, when electrophile attacks on the ortho position, so the carbocation will form, okay, when attacking is at the ortho position. Now, when the electrophile is attacking on the para position, then again the carbocation is forming after the attack at para position. But these carbocation which are ortho substituted and para substituted, they are stabilized by the resonance effect. So resonance effect shown by the chlorine is stabilizing the intermediate carbocation, because resonance effect is due to the lone pairs of electrons present on the chlorine, present on the halogen. Okay. So meanwhile, due to inductive effect, it is destabilizing the carbocation. Due to the resonance effect it is showing, it is stabilizing the carbocation also, particularly at the ortho and the para positions, because the electrons or the electrons donated by the chlorine through its lone pairs are localizing on the ortho and para positions, increasing the electron density of benzene ring at ortho and para positions, and you can say it will be easy for the electrophile to attack on the ortho and the para positions, and the carbocation which is forming, it will be stable due to the resonance effect. Okay. So you can compare now three of them, which we have just seen that due to inductive effect, the carbocation forming is destabilizing. The inductive effect shown by the chlorine due to the electron withdrawing nature. Meanwhile, due to the resonance effect shown by the chlorine, due to the donation of its electrons through lone pair, it is also stabilizing the intermediate carbocation. Now, if you talk about the deactivation, so overall effect of chlorine is deactivating due to the stronger inductive effect. So if you compare between the resonance and the inductive effect is stronger. Okay. So overall effect of chlorine is deactivating of the ring due to the stronger inductive effect shown by the halogen. And the ortho-para direction, if you talk about, that resonance effect oppose this inductive effect, stronger inductive effect at the ortho and para position, so that the incoming electrophile can easily attack on the ortho and the para position and form the stable carbocation. So this resonance effect making more reactive than the meta position. So resonance effect makes the ortho and the para position more available for the incoming electrophile to attack on than at the meta position, right? And resulting in the ortho-para directing behavior, and due to this slight increase uh, stability of the carbocation due to the resonance effect at the ortho and the para position, so that ortho and para positions will be available for the incoming electrophile to attack on due to the increased electron density at ortho and para positions of the benzene ring due to the resonance effect. Then at the meta position, so the resonance effect will be you can say considering, and the electrophile is attacking on the ortho and the para positions, and you are getting ortho para substituted products. Okay, or we can easily say that reactivity is controlled by the stronger inductive effect, but the orientation is controlled by the resonance effect, which is here is ortho para direction. Okay, so chlorine is an electron withdrawing group, we know, due to its inductive effect, but still it is ortho-para directing in the electrophilic aromatic substitution, which forms stable ortho-para substituted products due to the resonance effect shown by the chlorine through its electrons or lone pair electrons via resonance effect. Okay. Okay, let's solve our in-text question 6.8. The question is, in the following pairs of halogen compounds, which compound undergoes the faster SN1 reaction? So we have first part, second part. We have pairs. The first part have one pair where the first compound is a tertiary halide, or you can say a tertiary alkyl halide. Okay, so chlorine is attaching with carbon, which is attaching with other 3 methyl molecules. And you have the second structure where chlorine is attaching with carbon, which is attaching with other 2 CH2. Okay, so this is, you can say, stick model where we are representing the alkyl halides. And in the second pair, we have first structure where chlorine is attaching with this carbon, which is attaching with other 2 carbons. One is CH3, another is CH2. Okay, and in the second structure, the chlorine is attaching with the carbon, which is attaching with other 1 carbon only. Okay, so you have given this 2 parts, or you can say 2 pairs, and in this following pairs of halogen compounds, you have to identify that which will undergo the faster SN1 reaction. So you have given some time, try to analyze this question, and then we will see the correct answer. Okay, let's see. So for this question, first of all, let's understand the SN1 reaction. We know that SN1 reaction is a substitution nucleophilic unimolecular reaction. It occurs in the 2 steps. The first one is the slowest step, on which the rate is determined. That is, rate is determined by the concentration of alkyl halide, and the first step involves the formation of carbocation. First step is the formation of carbocation, and the second step is attack of nucleophile on the carbocation, on the stable carbocation, you can say. So the formation of carbocation here is a rate determining step. That means your carbocation stability is the key factor. So more stable carbocation, reaction will be faster, because rate determining step is the step where the carbocation is forming. So if the stable carbocation is forming, then reaction rate will be faster. Reaction will follow by higher speed at higher rate. So the order of reactivity for the SN1 reaction is highest for a tertiary halide, then for secondary halide, and then for primary halide. This we have derived from the stability of carbocation, because the tertiary carbocation will be more stable, then the secondary carbocation, and then the primary carbocation will be least stable. So more carbocation stable, more stable carbocation, the reaction will be faster. So tertiary halide reactivity will be faster, or you can say fastest, and least reactivity will be shown by a primary halide, which will give you a primary carbocation which is least stable. So if you see the first pair, we have given two structures. The first structure is a 2-chloro-2-methyl-propane structure. So we have a parent chain in which 3 carbons are there. First one is here, second one is here, and third one is here. And at the second position we have chlorine, and at the second position we have methyl group, CH3, right? So you can name it as 2-chloro-2-methyl-propane. Now if you see, the chlorine is attaching with this carbon, and this carbon is attaching with other 3 carbons. So this is a tertiary alkyl halide. Meanwhile, the second structure given in the first part of the question is 3-chloropentane. So we have 1, 2, 3, 4, 5. 5 carbon parent chain, where at the third position, from if you start from right side, if you start from left side, at the third carbon the chlorine will come. Okay. So at the third carbon we have chlorine, and we have 5 carbon parent chain. So we can call it as 3-chloropentane. And if you look upon it, the chlorine is attaching with the carbon with this, which is attaching with other 2 carbons. So this is a secondary alkyl halide. So this is tertiary and this is secondary. And we just have seen that SN1 reaction will proceeds via the formation of carbocation, right? And tertiary carbocation will be more stable than secondary carbocation. Tertiary carbocation will be given by this tertiary alkyl halide, because when this chlorine will be removed from here, this carbon will be tertiary carbocation. Okay, this carbon will get positive charge, and this is tertiary carbocation. And when you remove this chlorine from here, this carbon will get positive charge, and this is secondary carbocation. So SN1 reaction will proceed via the formation of carbocation. Alkyl halide first, which is given, is tertiary, and second, which is given, is secondary. And first, because it is tertiary alkyl halide, form tertiary carbocation, while the second will form secondary carbocation. And greater the stability of carbocation, faster is the rate of SN1 reaction performed by that carbocation. So tertiary carbocation will be having the greater reactivity, right? So tertiary carbocation is more stable than secondary carbocation. This is why the first structure, that is 2-chloro-2-methyl-propane, undergoes faster SN1 reaction than the second structure, that is 3-chloropentane. Okay. Now, let's see for your second part of the question, which is having again these two structures. The first structure is 2-chloroheptane, which is a secondary alkyl halide, because chlorine is attaching with the carbon, attaching with other 2 carbons. And this is a primary alkyl halide, because chlorine is attaching with the carbon, which is attaching with only 1 other carbon. So this is 1-chlorohexane, a primary alkyl halide. Now the alkyl halide first is secondary, and the alkyl halide second is primary. And secondary carbocation will be more stable than the primary carbocation. Secondary carbocation will be given by 2-chloroheptane. So that's why your first structure, that is 2-chloroheptane, will undergo faster SN1 reaction than the second structure, 1-chlorohexane, because it is primary. Okay. Okay, let's solve another in-text question, which says that identify A, B, C, D, E, R and R1 in the following. So we have given these reactions or group of reactions where this bromocyclohexane reacting with magnesium in the presence of dry ether, giving you A product. You have to identify what is A. Then when A is reacting with water molecule, you are getting B product. You also have to identify what is B. When RBr, that is alkyl bromide reacting with magnesium in presence of dry ether, you are getting C product. So you have to identify R plus C. And when C is reacting with D2O, you are getting CH3, CHD, CH3. The next reaction, which is starting from R1X. R1 is alkyl group, you have to identify what is R1. When R1X is reacting with sodium in presence of ether, you are getting this product, which is C, CH3, 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 single bond C, CH3, CH3, CH3. And when the same R1X you are reacting with magnesium, you are getting a product D. You have to identify what is D. And when you are reacting the D in presence of water, you are getting E, and you have to identify what is E. So A, B, C, D, E, and R and R1. These are the unknown compounds that you have to identify in these reactions. So you have given some time, try to analyze this question, and then we will see the answer. Okay, so for this question, the reaction of alkyl bromide with the magnesium gives Grignard reagent. So if you are reacting any alkyl bromide with the magnesium in the presence of dry ether, you will get a product as Grignard reagent, RMGX. Remember, we have studied about it. So Rx, any Rx, when reacted with magnesium in presence of dry ether, you will get RMG positive, X negative. If X is bromine, you will get RMG positive, Br negative. Okay. So alkyl halide reaction with magnesium gives Grignard reagent. Further reaction of this Grignard reagent with the water yields an alkyl group. So when you react this RMG positive, X negative, that is Grignard reagent, in the presence of water, you will get an alkyl group, RH. Also, the reaction of alkyl halide with sodium metal in presence of ether will give you a dialkyl. That means when Rx alkyl halide reacts with sodium in presence of ether, you will get dialkyl, R connecting with R, having great number of carbon atoms then present in the reactant alkyl halide, right? Or you can say double the number of carbon atom than the reactant. So these are general reactions we have talked about. Now we will see one by one what is happening in the given reactions. So this bromocyclohexane, when reacting with magnesium in presence of dry ether, so alkyl halide reacting with magnesium in presence of dry ether, what will you get? A Grignard reagent, right? Which is RMGX, that is cyclohexyl magnesium bromide. X is bromide and R is cyclohexene or cyclohexyl. Okay, so your A is cyclohexyl magnesium bromide, and when this is reacting in presence of water, it is giving you an alkyl, that is cyclohexane, that is your B product. Okay, so your A is your cyclohexyl magnesium bromide, cyclohexyl Mg positive Br negative, and B is cyclohexane. Now, when you see your second reaction where this RBr, okay, so your R is basically this propyl group, CH3CH3, okay, and this alkyl halide is 2-bromopropane, okay. When it is reacting with magnesium in presence of dry ether, you are getting a Grignard reagent. Okay, alkyl halide react with magnesium, you are getting a Grignard reagent, that is CH3, and the bromine is replaced by Mg positive and Br negative. And when this reacts with D2O, in presence of D2O, you will get an alkyl or alkane. Okay, so this magnesium positive and bromine negative will be replaced by D, that is deuterium here. So you will get CH3, CHT, CH3. Okay, and from this product, which is already given in our reaction, we have identified that what will be the alkyl group here initially present as an alkyl bromide. Okay, so from here we can guess that R is a propyl group, CH3, CH3, the same which is present here, because only the substitution is happening at the second carbon. The bromine is substituted by the Mg positive, Br negative, and then it is substituted by deuterium. Okay, so the R is your CH3, CH3 group, and C here is actually CH3, CH, Mg positive, Br negative, CH3. Okay, so C is a Grignard reagent, which is isopropyl magnesium bromide, and R is basically this isopropyl group. Now, lastly, for this third reaction, where your R1X is undergoing the magnesium reaction, let's reaction with the magnesium metal. So alkyl halide, when go with the magnesium metal reaction, it will give you Grignard reagent. So Grignard reagent you are forming is tertiary butyl magnesium halide, and when you are reacting it with water molecule, you will get an alkane group, that is 2-methyl propane. Okay, and when this R1X is reacting with sodium in presence of ether, you are getting dialkyl, that is 2,2,3,3 tetramethyl butane. This is the IUPAC name of this structure. And from this structure already given in the question, you can identify what will be your R1, because if alkyl halide is reacting with sodium metal in presence of ether, you will get your product as dialkyl. Okay, so only this single alkyl will be your R1. Okay, so you take this single alkyl and put here as R1. So your R1 is this tertiary butyl group reacting with magnesium. You are getting a Grignard reagent, which is your D product, and then it is reacting with water molecule, and you are getting alkane, 2-methyl propane. This is your E group. So you can say that R1 is this tertiary butyl group, D is your Grignard reagent, which is tertiary butyl magnesium halide, and E is your alkane, that is 2-methyl propane. Okay, so this is how you can identify A, B, C, D, E, R, and R1. Okay, let's see the summary that we have covered today. So halogens are orthopara directing towards the electrophilic substitution reaction. This we have seen. Different electrophilic substitution reactions of haloarenes we have seen, like halogenation, which includes the addition of halogen molecule in the haloarene molecule and give you the mixture of products where one is the para substituted one is major one and the ortho substituted one is minor one. In this reaction is happening in presence of anhydrous FeCl3, and chlorine positive is acting as an electrophile. The second type of reaction is nitration, where the NO2 group is attaching with your haloarene group, okay, haloarene compound, and giving you a nitro substituted paranitro and orthonitro substituted products. The paranitro substituted product is major and orthonitro substituted product is minor. This reaction is happening in presence of HNO3 and concentrated H2SO4. Here NO3 positive is acting as an electrophile. Next reaction is sulphonation. So sulphonation is happening when your haloarene is reacting with concentrated sulfuric acid, and you are heating this reaction mixture and getting the para substituted sulfonic group as a major product and ortho substituted sulfonic group as a minor product. Okay, so 2-chlorobenzene sulfonic acid minor, 4-chlorobenzene sulfonic acid major. Here SO3 will act as a electrophile. Okay, so these are different types of electrophilic substitution reaction of haloarenes. Along with that, fourth one is Friedel-Crafts reaction. First type is alkylation, where alkyl halide and aryl halide react together in presence of anhydrous AlCl3, gives you 1-chloro-2-methylbenzene and 1-chloro-4-methylbenzene. Again, the mixture of products, one is major, one is minor. Then you will get then you have the fifth type of electrophilic substitution reaction, which is Friedel-Crafts reaction. The second type of Friedel-Crafts reaction, that is acylation, which is actually you can say aryl halide reaction with CH3COCl in presence of anhydrous Cl3, and again you are getting mixture of products, the major one and the minor one. The para substituted one is major one, the ortho substituted one is minor one. Then we have also talked about the haloarene reaction with the metals, where the first reaction is Wurtz-Fittig reaction, reaction of alkyl halide with aryl halide in presence of the sodium metal and dry ether to give you a aryl and alkyl group combination as your major product. Okay, so alkyl halide reacts with aryl halides, and alkyl group and aryl group combined together give you your major product, and sodium bromide, or you can say sodium halide, will be here as a side product. Next type is Fittig reaction, where the reaction of two aryl halides are performing in the presence of sodium metal to give you diaphenyl or biophenyl as your major product. So you can see you are taking two haloarenes compounds and reacting them with sodium metal in presence of dry ether and getting a diaphenyl or a biophenyl as your major product, plus 2 sodium bromide will be the side product. Okay, thank you so much. That's all for today's chemistry session. Thank you.